Hello everyone and welcome to the Project Spotlight Passive House in Very Hot Climate. Many thanks to Norman Garcia for inviting me to say the welcoming remarks. My name is Laszlo Lepp and I am Senior Scientist and Managing Director of the Passive House Institute in Innsbruck in Austria. The headquarters is based in Germany, but we also have our second office in Austria where I am located. My main activities include consultancy and certification of all kinds of passive houses worldwide, but mainly in Europe and Asia. And so I had the honor of certifying the building in Bangkok, which is being presented today. The question is, what can the Philippines learn from Thailand's first certified passive house? Well, it's always a challenge to design and construct highly energy efficient buildings in a region where there is no practical implementation or experience available so far. A new climate, a new project team, questions about available products and materials, a potential gap in experienced companies. Being a pioneer is challenging, but these are exactly the challenges we have loved for over 3 decades at the Passive House Institute. Finding solutions for new situations, racking our brain to figure out exactly how to make a building efficient, sustainable, and future proof. This is exactly what has been achieved successfully in today's example for the first time in Thailand. Fortunately, we had an extremely committed local partner, which made our work as certifier much easier. I would like to thank Jay once again for his excellent cooperation on this project, which he provided as a passive house designer. Thank you very much. The first projects always require individual solutions, but we want to scale up in the long run. This requires suitable regional products, cost-effective solutions, and qualified professionals. That is the crucial point. Once the learning curve flattens out, special concepts like a passive house should become the norm. So I hope that many interested people will take advantage of the services offered by the PHI to improve their knowledge and skills, and that many companies will collaborate with us to optimize their products so that they can be offered then as passive house as a PHI certified components in the region and make the passive house buildings affordable. The implementation of real buildings is extremely important so that as many people as possible can visit such properties and see the advantages for themselves. Calculations using the PHPP, the Passive House Planning Package, and quality assurance in the form of the Passive House certification both play a key part in achieving maximum comfort, the lowest energy demand, and satisfaction for the occupants. I hope to see many excellent passive house designers, numerous certified passive house components, and a lot of passive house buildings realized in the Philippines in the near future. The foundation for this has been laid with Norman Garcia at the Passive House Philippines. And also other stakeholders like Jay from Taiwan and the PHI in Germany and Austria are ready to provide support. Before I conclude, I would like to invite you all to the next International Passive House Conference. We will be in Essen, in Germany, at the end of April 2026 to discuss the globally applicable passive house concept, showcase new developments, and establish new project collaborations. I would be delighted if we could all meet there in person. And now, I hope you enjoyed Jay's presentation about his experiences with the first certified passive house in Thailand. Thank you very much for listening, and I wish you all the best.
So this is the passive house approach. So if we combine passive house with low embodied carbon and electrify everything, plus we add clean energy, then that's the real climate action. So a little bit about myself. So I'm Norman Garcia. I'm the executive director of Passive House Philippines. I was once an oil industry civil engineer who oversaw the construction of gas stations across the country. Then I found myself shaken after watching Inconvenient Truth in 2020. So I literally cried, and I because I profited from the very industry accelerating climate change. And that guilt became fuel and began advocating for fossil-free building practices. Then after moving to Canada, I retrained as a building energy modeler and airtightness consultant. So since 2024, heat waves have forced the Department of Education to suspend in-person classes nationwide. And as you know, as you saw from the news, millions of Filipino students were already struggling compared to their South East Asian peers, now face further setbacks, with some suffering heat stroke and nosebleed in classrooms that trap more heat than they release. So families without air conditioning are left with impossible choices. So do they spend uh, on cooling or put food in the table? So it's very clear. Our buildings are not built for the climate we live in, but that's about to change. That's why Passive House Philippines is our organization. This is our organization. So Passive House not only deals with the energy. Of course, we need to deal with comfort because a building that is even if it's very efficient, but if it's not comfortable, people will not occupy it. And if a building is not occupied, it's not a building. It's called a monument, right? So thermal comfort is a infinite combination of indoor temperature and relative humidity. So we need to address both. So here's the scenario in the Philippines right now. So without air conditioning, uh, room temperature is high. At the same time, humidity is high. However, if we just blasted and cooled the air using standard air conditioning, yes, we lower the temperature, but the humidity is still high. But if we combine with if we dehumidify that air, then we can keep the temperature higher and the humidity the same, no? Okay, so before we talk about passive, so what's active? So active means it needs a constant supply of electricity to keep this water cold. On the other hand, a sports bottle, this is airtight, this is well insulated. If you pour cold water at 7 in the morning, you go for a hike to your favorite mountain, you open this sports bottle at 2 p.m. under scorching sun, it's still cold. It's because it's well insulated and airtight. Now, put that very same principle to house. So these are the five principles of passive house, and Jay will talk about this on when he talk on this project. So basically, the five principle: thermal insulation, efficient windows, air tightness, reduced thermal bridge, and last but not the least is mechanical ventilation with heat recovery. So thermal bridge is maybe something new to our Filipino designers, but basically a thermal bridge is something or a structural member that conducts heat from the outside going to the inside, and it's reverse in cold climates. So passive house, it's performance. It's meaning the building needs to meet certain performance requirements, contrary to prescriptive. So a passive house needs to meet these several criteria. So there are criteria on cooling plus dehumidification. So it should be no more than 15 kilowatt per meter per year plus variable allowance. And cooling load no more than 10 watts per square meter. And air tightness, there are two criteria for new. It's zero point 0.6 air changes per hour, and for retrofit, one. And of course, thermal comfort is very important in passive house. So it should be no more the frequency of overheating should be no more than 10% per year. So we have 365 days in a year. So meaning inside the passive house, um, the house should not overheat more than 25 Celsius at 36 days a year. And we also need to control humidity, and humidity is we measured in terms of absolute. So it should the limit is it should not exceed 12 grams of water per kilogram of air at a temperature of 25 Celsius. So this is the heart of the passive house. So as architects, as engineers, you design your house, and all of those parameters are entered into this software called passive house planning package. It's basically a very, very large Excel spreadsheet developed by very smart Germans. So, and it was purposely developed into Excel format because um, everybody knows Excel. So the learning curve is a lot easier than a customized software. So Passive House was developed in Germany. So note the house, Haus, it means building in German. So that's why you might be wondering why the spelling of our organization is like this. No? And take note, the word passive house, it's not trademark. If you build your passive house, as long as you use the passive house planning package, you do the energy modeling, it meets the criteria, then it's passive house. What is not allowed is what is trademark is the word certified passive house. And also, as Jay will explain later, passive house is not same as passive design. So Passive House was developed by Bo Adamson and Wolfgang Weiss. So can anybody guess the profession of these two gentlemen here? Are they architects or are they engineers? So yeah, so the answer is neither. They're physicists. So Passive House is based on building science, and there's a lot of research that are being shared by Passive House Institute to various Passive House practitioners all over the world. So Passive House has since it's originated in Germany, so in Europe there are many passive houses, but now it's starting to spread all over the world. Canada, US starting to spread, and on Australia, New Zealand, it's already growing there. And north of the Philippines, there are many passive houses there in China, Japan, Korea, and very few are in hot and humid climates like the Philippines. Um, and so right now there are only four passive houses in hot and humid climate. And with this growth of the passive house, in almost major countries in the world, they are passive houses organizations. So Passive House Philippines was founded last year, and hopefully we become a official affiliate soon. So passive house, it applies to all building types. So there are social housing, school buildings, kindergartens, gyms, office buildings, as a factory. In fact, those who were here on the launching last month, we featured the first passive house in Sri Lanka, which is the a garment factory. And these are the only known certified passive house in hot climates. So Indonesia, uh, Sri Lanka, which we featured last month, office in Dubai, and our feature project today, the first passive house in Thailand, which is a single family house. And hopefully, with this effort of the organization, you'll be inspired to build your next project as into passive house standard. So passive house is climate resilience. So this passive house made the news from the recent wildfire in LA. Entire community was gutted by wildfire, but a lone passive house survived. And since passive house is based on performance, it eclipsed energy performance of even the LEED Platinum certified buildings. So the question is, how do we scale this up? Okay, so we have a lot of professionals here from the renewable sector, but even if we put solar panels to every roof in the Philippines, it's not practical. It costs a lot of infrastructure. So the passive house approach is this is the hierarchy of low carbon design. So first, at the very bottom, reduce the energy loads through passive design. Okay, and then after you meet that, that's the only time you improve the mechanical system, and after that, then that's the only time you think of connecting to low carbon energy. So passive house has many crosswalk with the green building rating system. So just want to clarify, passive house is not a green rating system. Passive house is a standard for energy and comfort. So passive house has many crosswalk with popular green rating, such as LEED, Green Star in Australia, and of course in Home Star in New Zealand. And locally, we're hoping to get our local green rating, Verde and Green, to be on board as well. But hopefully that will happen soon. So be part of history by building the Philippines' first Passivized certified building. And if you do that, you'll have a lifetime membership to our organization, and you'll be a diamond sponsor for 10 years, plus a lifetime acknowledgement as Passive by Trailblazer in the Passive House Philippines History webpage. Okay, so that's a brief introduction on Passive House. So we are fortunate that our speaker is here, Jay.
Hi everyone, my name is Jay. I'm the lead energy engineer at BWK Green Architecture Design Company. Like many of you, my background is in architecture and architectural design. When our company first started, we mainly focused on passive house design. Over the years, through hands-on experience, we have gradually grown from being passive house designers to trainers and now also certifier. First of all, I would like to thank Norman for inviting us to share this project today. I also want to express my gratitude to Dr. Laszlo for his technical support, which has helped us step on step to better understand how to design and construct passive house in hot and humid climates. Today, I will introduce our passive house project in Bangkok. Through this project, I hope to inspire more designers in neighboring countries and regions to take concrete steps toward realizing passive houses. The project is an affordable housing development located in Bangkok, Thailand. It was completed in 2019 and constructed in accordance with the Passive House standard. This prototype building not only fulfills its purpose of providing affordable housing, but also achieves the goals of enhancing thermal comfort for residents and delivering significant energy savings. The project is a two-story detached family house with an unheated attic. The building construction is of a massive construction, reinforced concrete structure and lightweight concrete block walls. And the 3D floor area is 144 square meter. The house consists of a living room, kitchen, and guest room on the first floor, and three other bedrooms with their bathrooms on the second floor. As well as an attic, a four-person family will live in the house. Implementing passive house standards in affordable housing comes with unique challenges. The first challenge is the hot and humid climate. There are not many certified passive houses in such conditions, which makes each project a valuable learning opportunity. The second challenge is budget constraints. If we want more housing projects to adopt this approach, it is crucial to find ways to design and build passive houses that remain affordable and cost-effective. The third challenge involves the use of certain specialized systems that are not yet common locally. For example, insulated window frames and MVHR systems. The fourth challenge is ensuring proper training for contractors. Education and hands-on guidance are essential to achieving quality construction. Finally, we must also consider the behavior of future homeowners. Their understanding and daily habits play an important role in the long-term success of a passive house. According to local Thai clients and our own observations, local residents usually turn on the air conditioning only in the space they spend time in, and open the windows to partially achieve air exchange. As in other Asian tropical cities, this natural ventilation strategy is widely used, as it is believed that it could effectively decrease the indoor temperature and allow the resident to achieve thermal comfort. Although passive houses require the indoor temperature should not be than should not be higher than 25 degrees Celsius. Local people still believe that they can tolerate and feel comfortable at higher temperature. The climate zone is classified as a very hot zone, and there is no natural shading around the site. In Bangkok climate, there is no need for heating at all. The heating demand is zero. As you can see, the heating degree hour is 0. In Bangkok climate, there is no need for heating at all. The heating demand is zero. Regarding to passive house in cold climates, building comfort was mostly about keeping people warm in winter. Summer comfort was often ignored, and air conditioning became the easiest solution. But in hot and humid regions like Bangkok, the real challenge is opposite. We don't want heat from the sun or from inside of the building. Our focus is on blocking, delaying, and removing heat so that the indoor temperature stays comfort. So all our all our own all of our design strategy here are built around one simple idea: keeping heat out and keeping the inside cool. Between May and July, the sun shifts closer to the Tropic of Cancer. At this site, that means direct sunlight can come in from the northeast and northwest. That's why adding vertical shading on the north side of the building is still very effective. As we mentioned earlier, the passive house concept originated in Germany. Today, it has become quite common across Europe, Canada, the United States, and Australia. In recent years, we have also seen growing interest in Asia, even in subtropical and tropical regions with hot and humid climates. That's why exploring how to make passive house working in our part of the world is such a meaningful challenge. From this Google map, you can see that tens of thousands of certified passive house houses are spread all over the world. In addition to the project in Bangkok, we have also been designing and building passive houses in Taiwan. I truly hope that in the near future we will see the Norman and other friends in the Philippines creating your own passive house project as well. From this chart, we can see the energy demand for heating in a tropical existing building in Germany. For this For these older buildings, the heating demand is very high, around 160 kilowatt hours per square meter per year. When we move to low energy building, this drops to about 66. And for a passive house, the heating demand goes down to just 15 kilowatt hour per square meter per year. This is an incredible reduction, and we can also call it a nearly zero energy building. Now imagine if we add renewable energy sources such as wind power or solar panels, then it is possible to reach the level of a positive energy building, or even a building that can fully supply its own energy demands. And while this example comes from a cold climate country like Germany, the situation is actually very similar in tropical regions as well. The principles of energy efficiency and comfort still apply, just in a different climate context. Today, passive house certification is divided into three levels: Classic, Plus, and Premium. To begin with, every project must first meet the Classic standard. The Plus and Premium levels require strict, stricter limits on overall energy demand and cooling demand, and they also place higher requirements on renewable energy generation. You can think of it like earning medals in a competition. Classic is like the entry level, plus is like the silver medal, and premium is the gold medal. The more energy efficient and renewable energy you achieve, the higher the level. Because of time limitations, I won't go into detail about the definition of PER here. I will leave that to the expert to explain in the future sessions. So, how do we design a passive house? Before we dive into that, it's important to understand that passive design and passive house are not exactly the same thing. For example, when we talk about ventilation, passive design usually means nature, natural strategies like cross ventilation, night cooling, and so on. But in a passive house, ventilation is achieved through mechanical ventilation with a heat recovery. In passive house, there are many possible strategies depending on the climate and designer approach. But passive house is built on five core principles, as you can see from the slide, and you cannot skip any of them. From these five, you can extend other strategies and of course, their importance will vary depending on the climate. So, which one is better, passive design or passive house? Let me share my personal view. Of course, it's open for discussion. I believe that if we are serious about comfort, then passive house is a strong solution. Comfort depends on boundary conditions. For example, keeping indoor temperature between 20 to 25 degrees Celsius throughout the year, relative humidity between 35 to 55 percentage, carbon dioxide below 1000 ppm, noise level under 35 dB, and indoor air speed below 0.8 meter per second. It's very difficult, almost impossible, to consistently meet all these comfort conditions with passive design alone, because it relies too much on luck and external conditions. On the other hand, passive house can achieve this high quality indoor environment while using very little energy. So when we first entered the Thai market and constructed our survey, the idea of so-called passive design came up again and again. Local architects explained that they have been using certain solutions and methods for summer comfort for many years. However, many of these solutions turned out to be either less efficient or too expensive. That's why for this project, we decided to design strictly according to the five basic principles of passive house. First, insulation. Because of very hot climate in Bangkok, the air temperature can make the ground soil reach 29 degrees Celsius or even higher. So in addition to insulating the roof, it was also necessary to aid insulation to the walls and the ground. Second, low U value walls. Achieving a low U value in a wall in a wall is essential to reduce heat transfer. Now, some of you may not be familiar with the U values, so let me give you a simple idea. In a typical energy-hungry building, the U value is very high. For example, a wall made only for concrete often has a U value of around 3.5 watt per square meter K. That's quite common, but it means a lot of heat is coming through. Third, target U value for passive house. In passive house design, recommended in a passive house design, the recommended U value for the thermal envelope is below 0.15 watt uh, per square meter K. But in Thailand, the temperature differences between indoor and outdoor are smaller than in Europe, and the number of heating and cooling degree hours is also lower. So considering the budget, we allow for slightly higher U value that still balances performance and cost. So you can see the ground U value, the wall U value, and roof U value are slightly higher than uh, the U value suggested in Europe. We found this comparison quite fun. When we explain how insulation saves heating energy, we often use the example of thermos versus a coffee machine. A thermos has a very good U value, so it doesn't need constant reheating to keep the drink warm. That means less energy is used. In a tropical climate, the idea is the same, but instead of heating, it's about saving cooling energy. And to explain this, I like to use an example that people in Taiwan immediately understand: a bubble milk tea. If you put your cold drink in a single glass cup and a double glass cup, and then look at into through thermal image, you will see the difference very clearly. The single glass cup allows a lot of heat transfer because it has a poor U value. The double glass cup, on the other hand, provides insulation, so the drink stays cold much longer because it has good U value, lower U value. And next key principle is passive house window. In the past, insulate window frames and double or even triple glass window were very expensive, but as they have become more widely used, the cost has slowly become much more affordable. This photo here was taken at the International Passive House Conference, where I had the chance to see many of these window products in person. I really hope that next April, some of you will also have the opportunity to attend the International Passive House Conference and see them for yourselves. These two diagrams show how double glassing and triple glassing affect our sense of comfort in cold climates. Double glassing isn't quite enough. For example, where it is minus 14 degrees Celsius outside, the inner surface of a double glass window can be only 15 degrees, while the room temperature is 20.5 degrees, a difference of more than 5.5 degrees. When the radiant temperature difference is over 3 degrees Celsius, our body doesn't know which temperature to adjust to, so it feels uncomfortable. But when we upgrade to triple glassing with the window U value below 0.85 watts per square meter K, this problem disappears. The inner surface of a triple glassing window can be 18 degrees Celsius. The radiant temperature difference stays below 4K. The, the scenario described above is illustrated using Central European weather as an example. This slide shows the adjustment I made for Bangkok climate, and it's not from PHI. In the first diagram, you can also see that with a single glassing. You can see that with the single glass, when the outdoor temperature is 36 degrees Celsius, the indoor surface of the glass reaches 31.5 degrees Celsius. If indoor air temperature is 25 degrees Celsius, the radiant temperature difference is 6.5 degrees. Well, above the comfort threshold of 3 degrees Celsius. However, when we use double glazing with the U value between 1.2 and to 1.5 watt per square meter K, the indoor surface temperature of the glass is 27 degrees Celsius. Compared to the indoor air at 25 degrees Celsius, the difference is only 2 degrees, which is not only comfortable but also energy efficient. Different from the local single glassing and aluminum frame, double glassing or even triple glassing with a low E is necessary. This can greatly reduce solar radiation heat and conduction heat and reduce local discomfort. Avoiding including a huge amount of glassing area. Choosing low G value glassing, which is around 26% or lower, are always important for reducing radiant heat from the sun. In addition to concept of some shade applied to glassing, evergreen trees and fixed or movable shadings bring significant benefit for summer comfort. This picture shows how important shading really is. In cold climate country, even if shading is not perfect, sometimes the extra solar radiation can actually help by providing free heat from the sun. But in tropical countries like Thailand and Philippines, it is opposite. Without proper shading, the cooling demand from air conditioning can become extremely high. That's why I always remind architects, whenever you design a window, design the shading at the same time. For east and the west-facing window, using vertical shading. For south-facing window, use horizontal shading. And also pay attention to the surroundings. Sometimes nearby mountain trees or even buildings can provide useful shading too. The original purpose of MVHR, mechanical ventilation with heat recovery, is to provide a continuous supply of fresh air. Indoor spaces accumulate pollutants over time. This could be toxic substance or simply unpleasant odors. The best ways to remove this dirty air is through ventilation. Some people suggest that simple opening window can achieve ventilation and lower carbon dioxide levels. However, what we emphasize here is that the system must be effective and continuous. Even if occupants forget to open windows, mechanical ventilation can still ensure good indoor air quality. It is important to note that passive house do not prohibit opening windows. Additionally, when there is a demand for heating or cooling indoors, we want to minimize energy losses during ventilation. That's why mechanical ventilation systems incorporate heat recovery features, namely HRV heat recovery ventilation and ERV energy recovery ventilation. In high humidity environments, ERV systems are necessary because they regulate humidity, providing a form of passive dehumidification. Note that this is not the same as a conventional dehumidifier. However, in extremely humid conditions, a dehumidifier may still be needed. These two diagrams help explain the differences between passive design and a passive house. With natural ventilation, we rely on wind, temperature differences, and timing to refresh the air, but it comes with many limits. Take Bangkok for example. Outdoor temperatures are often above 25 degrees Celsius, so opening windows just let hot air in, which make air conditioning work harder. On the left picture, outdoor pollutant can easily get inside, and there are other issues like noise, high humidity, security concerns, and cost. That's why relying only on natural ventilation cannot give you both comfort and energy saving in this climate. From these two floor plans, you can clearly see that AV space where people spend most of their time, like the living room, dining room, bedrooms, receive fresh airs. You can see that living room and dining room and bedroom receive fresh air. The kitchen and bathrooms have return air. Kitchen, bathroom, and second floor bathroom. bathroom. So we have to ensure that every room in the house gets proper ventilation. The location of the mechanical ventilation units is placed above the kitchen, installed above the kitchen. The outdoor air pipe and the exhaust pipe are wrapped by 2 centimeters of insulation and were kept as short as possible. Each supply air outlet has a silencer. So basically, the ventilation planning is based on passive house core concept. In this project, we made the system a little bit more complex. Initially, I would recommend having MVHR, air conditioning, and a dehumidifier as separate separate season parallel seasons. This not only makes maintenance easier, but also helps designers clearly understand the purpose of each season. What you see here is so-called a compact unit which combines both ERV and air conditioning functions. So the first animation shows the ERV operating, and the second shows the air conditioning in action. So you can see the outdoor unit and indoor unit. The indoor unit was installed above the kitchen. So the first animation shows the ERV operating. So outdoor air, fresh air, but hot air come in. But indoor, it's red air from the bathroom, from the kitchen. It's cold air, but dirty air. So they do heat exchange it here. Then dirty and hot air going to be pumped out. Then fresh air and cold air will come in. So second animation show the air condition in action. As mentioned earlier, the indoor unit is installed in the kitchen ceiling. Since it includes air conditioning, the heat pump is placed just outside the kitchen. Many people may wonder why don't you install this kind of system in your own house? The answer is that its cooling capacity isn't very high. As you can see here, the cooling capacity just 3.5 kilowatt. If a building has high cooling demand, this system isn't suitable. But because we first designed the building to achieve nearly zero energy demand, this product works perfectly for our needs. Okay, so you can see here, we make the building cooling load just 9 watt per square meter. And 3-floor area is 144 square meter. So this machine compact unit, its cooling capacity is already fulfill what we need, and a little bit much higher what we need. Thermal break. Thermal breaching is also a key issue when we want a building to reach nearly zero energy. It's not only about losing energy. When thermal bypass happen, condensation can form. Over time, this leads to mold growth, which damage the structure and can even cause respiratory health problems. In this photo, the problem happens at the balcony slab connection. Because of structural safety, the insulation cannot continue through the joint. The insulation an indoor slab and balcony slab. As a result, heat escapes through the slab. The indoor heat can escape through the slab. This is one of the most common thermal breach problems we face. In hot climate, external heat can easily enter the balcony connection. So this picture showed what happened in cold climate. So in hot climate, heat can bypass the insulation through the slab. Get in. These images are notes I took during the International Passive House Conference. You can see that a thermal break device was added between the two slabs, which greatly reduced the thermal transfer between indoor and outdoors. Okay, thermal break. It's indoor and outdoor, and this indoor and outdoor. The diagram in the lower right corner shows the installation method more clearly. Before we cast the concrete, you put the thermal break device between indoor slab and balcony slab. In Bangkok, however, we approach this differently, as you can see in the diagram at the bottom center. We separate the interior slab from the balcony slab, indoor slab and balcony slab. By doing this, a linear thermal bridge is transferred into two-point thermal bridge. That's a linear thermal bridge, and then it becomes point thermal bridge and point thermal bridge, which then allow the insulation to pass through. Okay, so insulation can go through this. This is more cost-effective solution we propose for addressing thermal bridges. Of course, you may have your own strategy in the future. In this project, we also spent a lot of time doing thermal bridge simulations, following the PHPP manual, the number 15, 16, 17 thermal bridge types, and the window installation thermal bridges. As I mentioned from the last slide, it's interesting to reduce the cost of thermal break. We discussed with the structure technician to separate the balcony floor from the indoor floor so as to change the linear thermal bridge to kind of point thermal bridge. Keep the core idea of the continuity of the insulation. So you can see the slab. Linear thermal bridge, we separate it, only have the point thermal bridge, and that the insulation goes through all the opaque wall. Airtightness. Achieving airtightness is never an easy task, but let me explain why it is so important. When we talk about MVHR, HRV, or ERV, mechanical ventilation with heat recovery, this is what we call regulated ventilation. Regulated ventilation. That means you can precisely control how much fresh air comes in, adjusting it according to the number of occupants or the size of the space. Air leakage, on the other hand, is unregulated ventilation. Unregulated ventilation. You have no control over how much air is coming in. It could be cold air in cold climate or hot air in hot climate, and it can also bring in bring in polluted air. So in we invest in a high efficiency ERV system. It is essential to also improve airtightness of the building. Otherwise, the performance of such an efficient machine becomes almost meaningless. Okay, we choose high efficiency ERV system. So at the same time, we need to improve airtightness. As mentioned above, the design of the MVHR and the airtightness of the building envelope also consequently become important, especially when we consider mechanical ventilation system. Those unregulated ventilation should be decreased. However, the reduction of potential unregulated ventilation provides quite a different concept from the local building construction style. Because the project is made of concrete block with a mortar screening, the envelopes are already airtight, the wall already airtight. So we spend more effort focusing on the airtightness of the places in which the air ducts, electricity pipes, and water pipes penetrate the walls and deal with possible air leakage in the installation of the window. Whether or not a building achieves Passive House certification depends on passing the airtightness test. Both depressurization and pressurization tests are required. Please refer to EN 13829 if you are interested in technical details. Other strategies. Providing shade on opaque wall can also partially reduce radiant heat absorption. Therefore, we build a 3D model using dynamic simulation software to estimate the reduction factor of shading for each wall in order to obtain more accurate input data. Here, the term reduction factor refers specifically to shading applied to opaque walls, not to glassing. I remember someone once asked why exterior walls are often dark and whether using highly reflective paint can reduce heat absorption. The answer is yes. Lighter color walls can help lower the amount of heat that absorb. This is especially important in hot climates, where keeping walls from getting too hot matters a lot. However, insulation should always come first. Coatings or shading should be added only after the walls are well insulated to keep the building stay cooler. So from PHPP, you can see different color have different exterior absorptivity. So that's why we suggest white paints, okay? Because absorb less radiant heat. But now, PHPP consider more. Even it's a white paint, but because the building used for a very long time, it may accumulate some dust. So exterior absorptivity, this data, the number might change a little bit. Other strategies. In the PHPP software input, the default setting of internal heat gain counts from 2.1 to 2.4 watt per square meter. But in fact, we can still do more than that. For example, we encourage the resident to choose high-efficiency electronic products. Second, those appliances which would generate a lot of heat while operating, such as washing machine and clothes dryers, are installed outside of the thermal envelope. We keep it outside. So from the PHPP, you have to input, do you use it or not? And also, did you keep it indoor or outdoor? Also, instead of using hot water tanks, that will increase a lot of internal heat gain. Instantaneous electric water heaters are other option. Hot water tank is quite common in cold climate. They put the water tank indoor. But in hot climate, I won't suggest that. Either we just leave it outside, or I would suggest use like instantaneous electric water heaters. Next, more than that, we shorten domestic hot water pipe as quick as possible. So from the drawing, you can see we shorten the water pipe length. Why? Because passive house is really very close to nearly zero energy building. Any heat appear inside is not allowed. Okay, so that's why we need to shorten domestic hot water pipe. From the design, we try to make it as short as possible. Okay. According to PHPP calculation, the energy balance of the building was as follows. It can be sure that this project does not need to use heating to maintain the temperature above 20 degrees in winters, which is expected in terms of the climate in Bangkok, Thailand. On the other hand, we need to active cooling to cool the house year round. The cooling load target 10 watt per square meter is achieved via not only the five principles of the passive house design, but also through shading. Good shading is provided by the use of balances along the sound walls, less window area in east and west, and suitable vertical shading in the north reduce the cooling load and demand. To conclude my presentation, I would like to mention some innovation that my company is working on with the intention to implement in the future. In general, we pay attention to installation of ventilation pipes and hot water pipe to avoid waste heat affecting the indoor cooling load. In future, we would also recommend that the storage tank and water supply pipes outside the building could be covered and insulated. The reason is that the water stored in the container left outside could absorb significant heat, which then is transported into the house via the taps. In Bangkok, we will always need active cooling due to the fact that building is a passive house. A combination of the ventilation system and a cooling heat pump could be a solution. The ventilation unit in the kitchen with the heat pump outside can cover the demand. However, for local residents, the use of one external heat pump and mini split unit in each room is usually their preferred solution. This could be related to the fact that it provides residents with direct control of their environment. So this is what we did in Bangkok project. But local people in each room sometimes they like to adjust their temperature. So split the mini VRV system. Therefore, providing a ventilation system and a mini split installation with separate parallel ducts might still be a good options in the future. In future research, choosing an environmentally friendly thermal insulation material is another goal of ours. Taking a local aquatic plant as an example, this plant is invasive and causes disaster of nearby reservoirs and rivers. However, we found that this plant can be made into an insulation material that has very low thermal conductivity. So when we use it as an insulation material, we can not only solve ecological problems, but also find a direction for affordable passive houses. Thank you and have a great conference.